Hello everybody. Today we're going to introduce the concept of linear regression. Before we do that, and I should be apologizing right now, the later videos will definitely get into linear regression, but we want to get to the backbone of linear regression, which is covariance and correlation coefficient. As you see in the screen in front of you is my formula sheet. And what I have on here under my linear regression assumptions, there are these two formulas, covariance of xy and the correlation coefficient r, which is the division of the covariance measure divided by the standard deviation of x and y individually. Some people think of correlation as a ratio of the measurement of the spread between two variables against the measure of the spread individually. It's kind of a ratio of those two. And we'll see that as we develop these formulas and talk about the concepts of the covariance and the measurement of R. Notice to get R, you need the covariance. Please notice that, right? Covariance is the numerator of R. So as we work on the covariance, I am thinking about building the formula for R as I do it. All right, let's get right into this game. So example 1, I have price of the home and $100,000 there in the left column. I have days to sell on the right side. So the question is, can the price of the home predict how long it will take to sell? That's the question. Can the price of the home predict how long it takes to sell the home? So the first thing I always try to understand in my questions are, what is the X value and what is the Y value? Well, if I'm using X, the home, to predict the days to sell, and that's the key, what I'm trying to predict is always my Y, then that's my order, X, Y. By the way, if you're utilizing Excel like I am, always make sure your X is on the left. If your X is not on the left, you're going to have an issue when you do the scatter plot. Because in fact, the easiest way to get your simple answer is to build a scatter plot and add some details, and the information you need comes automatic. What do I mean by that? Well, let's get right into it. If I highlight my data, and I want to draw a diagram, recommended charts, scatter should come up. If it doesn't, go to all charts and find scatter. So here's my scatter plot. Let's bring it out. So this is my scatter plot for my example 1. Not bad. It looks like my data is roughly in a linear line. So it seems like linear regression might be a good option. But before we get into any of that in my future videos, I want to talk to you about how can we measure the strength of this linear line if there was a linear line that passed through this data. For example, to kind of jump ahead but then come back around, if you're on the picture, you may add a trend line. On your scatter plot, you may add a trend line. What I do when I add the trend line is I go to more options. I like to use the more options because everything is listed. Do you want an exponential, a linear, a log, a poly? Which one do you want? We want a linear. R is typically used for measuring linear strength between two variables. So I have linear. Now, I'd love to display the equation of that line and the R value. And so they both come out. And here they are. Short and to the point, we have the equation of that line. That dotted line is right there. And we have the R squared value. I'll let you again look at my future videos to really see what they represent. For us right now, I wanted to be able to get to the R value quickly. And notice we have the R squared value. From here, we can take the square root, and the R value is that quick to have. The R value is that close and that quick to have. Of course, Excel automates most of this stuff. So if you want the correlation, there probably is a formula. You just got to start spelling, and there it is. Of course, what I always do before I utilize a formula is read and see what it does. Returns the correlation coefficient between two data sets. That's what I want. So we open the parentheses, scan in the first numbers, just the numbers, comma, scan in the second set of numbers, and we will find our value for R. There is our correlation coefficient R. By the way, that's R squared. And so if you took the square root of this, that would be that number. Your choice on how you actually get it in real life. If you want to have both, that was funny. Got the registered symbol. Guess it didn't like me doing R there. Nope, not going to work. Fine. Correlation symbol R. How's that? So the correlation symbol R is 0.977. What does that mean? What that means is the points are really, really closely packed around the line. The prediction line picked, and again in future videos we'll talk about the prediction line picked, but this prediction line, that dotted line, these blue dots are really packed around. And notice, these blue dots are really, really close to that line. And you can check out a residual to see how much error there is. Again, in future videos, as I go into details on regression analysis, prediction, residuals, you'll learn about all of these. I'm trying to stay really close to what is the correlation value. And more importantly, how would one get the covariance to then get to the correlation? That's what I want to get into. Yes, I know it's easy. Look, I just did it right now. I got the correlation number, the R squared value, which led me to the correlation number. The correlation number is 0.977. Short to the point, it means I have a very strong linear relationship. How good is my prediction? How good is the correlation? That's why you got to listen to my later videos to understand the residuals and the checks to make sure this is an accurate usage of correlation. We're just trying to find the measure of covariance in R right now. That's really the biggest brunt of this video. And actually, it's the backbone of what we do, is understanding correlation and covariance. So covariance, it's a formula, as you see right there. And by now, you've done enough Excel. You should be able to pause this video and build that formula for me before I do. That is, you should be able to build the x minus x bar, y minus y bar product divided by n minus 1 before I do. So pause the video and try it out, and then I'll be back. All right, I'm back. So what do we need here? I need an x minus x bar. I need a y minus y bar, and I'm breaking it into small steps, okay? You don't have to do this if you're really good with Excel. And then there's going to be the product that we needed in the numerator. So that's the numerator, right? The product is the numerator. I'm breaking this down because I want you guys to have there's two things we're learning here. Really good Excel skills, and on top of it, understanding the statistics behind regression. So x minus x bar. Well, to find x minus x bar, I probably need x bar, right? The average of x. That would probably be really, really helpful to have. So let me find the average of, let me keep it in the system that I have here. Let me find x bar. Let me find y bar. Well, x bar by definition is the average of the x's. That's what x bar represents, the average of the x's. Got it. What is y bar? Well, y bar is the average of the y's. Got it. Now, yes, what am I doing? I'm going a long way to get to this number. But I want you to understand how the formula works. That's really what I want. I really, really wish you understand what it means to be covariance, which then leads us to correlation. I'm trying to make you understand what correlation actually represents, what it measures. And by going through the formula, you get a feel for what it measures. So first, we find the average for each column. And then you take each variable in each column and take away how far it is from average. That's what it says to do. And since the B value is always the same, that is x bar is always the same, I'm going to absolute reference that number. Now in real life, you probably just quickly get the correlation and you're happy. But I'm trying to teach you what the correlation is and how it works. So the first thing you got to understand is what we do, the numerator of correlation is the covariance. The covariance measures the strength of the relationship in the prediction. And what do I mean by that? Well, it looks at each x value, and it looks at how far each x value is away from x bar. That's what we're doing here. And then each y value, and how each y value is away from y bar. So we're looking at how each point is away from what we'll call the quote-unquote average point, x bar, y bar. That's what we're doing, is we're looking at how far they are away. We're kind of measuring a spread. How far off are my x and y away from x bar and y bar? Notice that, right? These 2 points, how far are they off from the average point, x bar, y bar? This would be the average point in my graph. If I could plot it, the point 315, 136, right, would be the average point in my graph. And I'm trying to find the distance each x and each y is away from this average point. Once I've done that, then I'm going to look at its product, because if I don't, I get zeros and that's not useful. So I look at its product to kind of try to get a weighted average distance in some respects. So I'm going to look at the product of each one of these. And so that is close to the numerator. That's the product of each one of these. So this is kind of like a square distance if you look at it. This is really sort of a square distance away from the average point in some respects. Now, recall the formula. The formula is to, again, you take x minus x bar, y minus y bar, product, did that. Now I got to add them up. Oh, I know how to add. All right, we know how to sum, right, guys? We know how to sum. That was awesome. We need to sum this up. So we're really, if you're thinking about it, building some type of average, some average square distance away from the average point. And that's really what we're doing. We're trying to find the average square distance away from the average point. Kind of a squared variance, not squared variance, but in some respects, a variance. And so that's why this is called the covariance. The covariance, because you're measuring both x and y, not just one variable. One variable will be the variance. We're measuring this average distance spread by the two variables. That's why it's a covariance. The covariance is this sum, the numerator, there it is, the numerator, divided by n minus 1. Well, now we need to know what n is. Well, n in this case, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 values, so I'm going to use 7 here. And so that is the covariance measurement for this example. Now, yeah, you could have done n, and you could have done count. And count, what it does, it just counts the numbers in your set. And yes, there are 8 numbers in my set. So my covariance, if I want to automate this, not equals, would be n minus 1. And so, yeah, same number represents. Awesome. So there's the measure of covariance. It's the, think about, remember what variance was. It was the average square distance. Same idea for covariance. It's the average square distance between my point and the average point. So if you understand variance, then you'll understand covariance because they're very similar. But see, the problem with covariance is the units can be huge. Notice this. The covariance is 1524. You want to know what that tells me? I have a strong positive relationship between x and y. And I shouldn't even say strong. I have a positive relation between x and y. That's really what I get from this information, is there's a positive relationship between x and y. I don't know how strong it is because I don't have a ratio to identify how big is 1524. This is the downside of the covariance. The covariance does measure whether you have a positive relationship or a negative relationship. If the covariance is positive, you have a positive relationship. Positive means as x increases, y increases. If the covariance was negative, then you'd have as x increases, then y decreases. That's a negative relationship. So again, in this case, we have a positive relationship for the covariance. Awesome. You're asking me, is there a covariance formula? Well, let's check it out. COV, oh look, covariance, and we're looking at a sample. Let's check it out. Covariance of S, highlight your numbers, comma, highlight your numbers. Let's see if it works. Oh look, it returned the wrong one because I was using the sample. Let me guess, if I change this to backspace P for population, I get sort of the same number, but it's rounded. I'm kind of curious in the formula why these are not matching. Hey, everybody. What you don't know is I took a brief vacation and I fixed what was wrong in my Excel. So because you got to think the Excel formula should work. And this was a sample, so I should have been using covariance of sample, which I am using now, the covariance of the sample. I paused in the video for a moment, and I looked back at my formula, and I had made a mistake in my formula, a very simple, basic mistake, and that's why it's good to have Excel to back you up, or any technology to back you up. My simple, extremely basic mistake is if you don't have a parentheses in my formula around the denominator, it would have done the division, then subtracted 1. I wanted the subtraction 1 before the division. That's the formula, is to subtract 1 before the division. I needed the parentheses in place, or else you would have never, ever gotten the same exact number. And it should. The formulas in Excel should work. So it's a good thing I paused and checked, because, I want a good, clear lecture for you guys on covariance. So yes, you could do it this way so you get the idea of what it really feels like. Or yes, quick to the point, there is a covariance of the sample. It's covariance.sample. Excel is a wonderful thing. Now that I have the covariance, I can then move on and find the correlation number by hand if I so choose to. What I'm doing is just trying to get you used to, before I just quickly boom, 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 nail these out, I want you guys to understand how these are built, how the measurements are built. So what we have here again is we have this measurement of a relationship. The problem is this measurement is really out of whack. You don't know how strong it is, because this number could be as big or as small as you want based on the units you're working with. And units are important. If I had used thousands here, this number would balloon up big time. And so all you really get from the covariance is whether there's a positive or negative relationship. That's good to know. But I'd also like to have some type of relationship that measures how strong the relationship is without the units being a bearing on my answer. Again, the covariance, the units matter big time. The correlation, there are no units on correlation. It's like the z-value. There are no units on it. It's just a strength measurement. And so what I could do here is, if I could take this and offset it with some kind of spread value that will offset it to give me this unitless measurement, I want to do that. And that's where the formula for correlation comes from. Correlation, you have this covariance measurement, but we're going to offset it with this product of the two spread values for the sample standard deviations of each of the x and y value. And so I need those. So I need the standard deviation x and the standard deviation of y. And so the standard deviation of x, I'm going to find it classically, standard deviation of S, standard deviation of your sample. The reason why I keep picking S is because I have a sample. So the standard deviation of X is voila. The standard deviation of Y is voila. And I get the two standard deviations I need. So by definition, the correlation, by definition, is this ratio of this covariance, which is this average spread squared distance. Square distance. So if I'm going to really offset it with unitless, I would need two measurements of spread. And these are the two measurements of spread. And when I'm to multiply them, I get also a square distance of spread. And hence, when I take a square distance of spread divided by another square distance of spread, I get this unitless feature, which is known as the correlation. And so now we get this number 0.977. It not only tells me it is a positive relationship because the correlation is positive, but it tells me the strength. And how does it measure strength? It measures strength because correlation is bounded between -1 and 1. The closer it is to the edges, 1 or -1, the stronger the relationship. The closer the number is to 0, the weaker the relationship is. So because this measurement is 0.977, it makes sense to me that these dots are really close to the prediction line. And that's what it represents. These dots are extremely close to the prediction line. And so this strength, this correlation makes sense. It is a very strong linear correlation. Now, I have not done any checks on regression. Please note, I have not done my linear regression checks. That'll be in future videos. Today's video is understanding what the covariance does and how the covariance has an issue with units. So we do a division by these standard deviations, standard errors, so I can get this unitless feature called the correlation. And that's really the theme of this. What is the correlation? What does it measure? Well, the correlation is a measurement between -1 and 1 based on that division. And this is a unitless measure. So it just measures strength of linearity. And the closer it is to 1, the more stronger and positive I have. Positive mean as I go left to right, I see an increase in the trend line. Strong because the dots are really connected to the prediction line. Awesome. Now that I've done it once with the formula, you can either do it again via the formula, or you can use the Excel tricks. I would do it both, so again, you get to appreciate how to build the formula. You really should have Excel skills and be able to follow my work to get to these formulas as true. Of course, we want the correlation and the covariance fast. Nothing wrong with that. The covariance is a measurement, covariance, of the sample, and you got to know if you're working with a sample or standard deviation, sample or population. We have a sample because by defined we are usually sampling in our class, so we're sampling. I'll let you know if we're dealing with a population. If you're dealing with a population, that means you have every single item that you're searching for. Typically, we don't have all values, so we have a sample. And since we have a sample, we can quickly get the correlation and the covariance. Notice, the covariance, again, is a measurement of do you have a positive or negative relationship. According to the covariance, we have a positive relationship. According to the correlation, we don't have a really good relationship, linear relationship. Well, let's check that out with a graph. Highlight the data, insert, recommended, scatter, and just pause for a moment. Does everybody see why a linear line would not be a good prediction for this graph? And that's what the correlation's coming up with. The covariance didn't see that. Covariance just says, looks like as you go left to right, you have a positive relationship. Well, that's true. As you go left to right, it gets more positive of a relationship. That's true. So the covariance is still doing its job. The correlation is saying, yeah, but the linear relationship is not there. As you go left to right, I don't think a linear relationship is what you're looking for there, boss. And that's why it's important to have other classes in statistics. This is clearly a non-linear relationship that I've picked. And true, notice the title, non-linear. Well, why do I do this? Why did I do this? Well, to make you understand, you can't just willy-nilly pick off the correlation and go, ooh, it's not linear, I'm done. You have to also look at the graph and understand sometimes lines work for prediction, sometimes non-linears work. And in fact, go to my plus, go to my trend line, go to more options, I would pick the polynomial. Because I've been trained, that's a quadratic. That's a nice x squared. But let's check out what it is. Display the equation. Display the r squared of the equation. And notice what you get here. Yeah, you get x squared plus 1x plus or minus some error there. Don't worry about that. And r squared is 1. Well, look, your prediction line is almost on top of this. And yes, I made this data up. I squared each number plus 1, okay? All right, so I knew the graph. Your r squared, though, is not linear prediction here. Your r squared is how good the squared is prediction. I want you to understand, this r squared does not represent linear prediction anymore. This r squared is all about the prediction when it comes to utilizing the x squared. That's advanced statistics, and you can stay tuned to my advanced statistics videos if you want to look more into that. We will be studying linear regression in our first level stats class. You want to go to nonlinear, stay tuned to my nonlinear regression models in the advanced stats class. But please, this is a video on correlation covariance. The covariance said there's a positive relationship. There is. Look left to right, it gets more positive of a relationship. True. The correlation says, yeah, but there's no linear relationship there. And I agree. The linear prediction line, where is it? There's no line that really best fits this data. If you're using a line, you're doing it wrong. Because as soon as you plot the data, by the way, that's one of the checks you'll learn in future videos. First check, draw the picture. If the picture looks like this, R looks like a good thing. Linear regression looks like a good idea. If your data looks like this, linear regression is probably not your best choice. Nonlinear regression or some nonlinear transformation is probably a better choice. Those will be saved for later videos. But, one more time, this video is all about finding correlation and covariance. How does one find the covariance? You could do it by hand, and I showed you. If you have to do it by hand, nothing wrong with that. Covariance can be gotten by formula, because in Excel, just got to know the Excel formula you want. And once again, we have a sample, so we throw it in. Wow, pretty positive again. Means we should have a positive relationship. Let's check out the correlation. The correlation of my two variables is, voila, pretty big and positive. Not as positive as this, so I expect some scatter. So what I would do, I draw the picture. I bring the picture into the game. I always try to bring in the picture to really understand what I'm working with. So recommended chart, there we go. There is my chart. And I can understand now why the correlation is slightly strong positive, but I also got an issue. Please notice my graph takes a major right-hand turn, a vertical turn at the last point. Some would think that's an outlier. And so we could look into if it's an outlier utilizing Cook's distance, again, an advanced feature, but we have ways of investigating outliers in scatter plots. Please look up Cook's distance if you want to do that in my advanced feature videos. Right now, I'm just looking at correlation and covariance. My correlation says 0.75. It's not that strong. But I contend if I drop this value, I wonder if I drop that value and say if I measure the numbers that are all the numbers except for the last one, if I inspect the correlation before it, look what happens. My measurement for correlation goes through the roof, gets really close to 1. And that means I have a very strong relationship as long as I focus in on the values before the last point. It seems like this last point, and look at what the last point did. The last point dropped my correlation by 0.23, right? That's a difference of 0.23. That's a very measurable difference right there. So some would say maybe we do our modeling without the point, but we tell everybody we did that because there's a potential outlier. And again, to measure outliers, you have to look at Cook's distance, and you can see that in future videos. My discussion today is centered around what covariance and correlation does. Covariance just measures whether the relationship between the dots are positive or negative as you look left to right. Each time I did a positive relationship. All right, the correlation is a strength of linear relationship. And what it's saying here, in this case, is there's a pretty strong one, but because of that last dot, that influential point, I bet you my prediction line gets off track a little bit. Where if I just keep to these first few points, I'd be really tightly packed, just like my first example. All right, guys. This was my introduction into correlation, into covariance. Please stay tuned to the regression videos to see a full-scale attack on regression analysis. Thank you, guys.